Unit 4, pages 120 to 125. We're going to continue on with our related rates. So on page 119, we completed the table where we wrote the derivative for all of those geometric formulas, and now we're going to use those derivatives and or calculus to actually answer problems, which are called related rates problems. So for 120, we have the problem: an air is leaking out of an inflated balloon in the shape of a sphere at a rate of 230 pi cubic centimeters per minute. At the instant when the radius is 4 centimeters, what is the rate of change of the radius of the balloon? So there's a few things that I want to do before we even get into the steps for solving this problem. First thing is annotate this problem. So we know that air is leaking out of a balloon. So we know that something is going to be negative. We know our balloon is in the shape of a sphere. It's really important. That gives us an idea of what kind of formula we're going to be using. We have a rate of 230 cubic centimeters per minute. So if we're looking at cubic centimeters, then we know that we're talking about volume. And from page 19, we know that dt is the rate of volume. We also know that there's an instance when the radius is 4 centimeters. So at some point, r is going to equal 4. Although we know that in a sphere, the radius is not constant, right? It's changing as the sphere gets bigger or smaller. But at some instance, we know that the radius is going to be 4. And we want to know the rate of change of the radius. So this means we need the dr dt is what we're looking for. So first part of solving a related rates problem is identifying all the variables involved in the problem. So we know that one variable that we have is the radius, and the other variable that we have is the volume of a sphere. Okay, so it's important to know the shape that we're talking about because that will help us to determine which formula to use. We also want to know if any of the variables of this problem will remain constant. So we only have two variables, radius and volume, and we know that neither one of those is going to stay constant, so we have no constant variable. Okay, so now we want to identify the rates that are given and the rate that we wish to find. So when we annotated this problem, we had two rates. We had dv dt and we had dr dt. Right, one of which is given to us, the other is the one we wish to find. So dv dt was given to us, and it's 230 pi centimeters cubed per minute. There's also a really important piece of this that we found out at the very beginning of this problem, which is that air is leaking out of the balloon. So our volume is actually going to be negative because it's going to get smaller. So the rate is decreasing. dr dt is what we need to find. And the units for dr dt are going to be just centimeters per minute. Right, because our unit of time in this problem is minutes. And radius is not going to be centimeters squared, that would be area. And centimeter cubed is volume, so centimeters is the length of a radius. So this next piece, part 4, we want to write an equation, often a geometric formula or trigonometric equation, that relates all the variables in the problem for which a rate is given or for which a rate is to be determined. We're going to substitute any value that represents a variable that is constant throughout the problem, which we don't have, so we don't have any constants. And it is important to keep in mind that you can only have one more variable than you have rates. You may have to make a substitution that relates one variable in terms of another. So let's double check this in our problem. So we have two variables. We have r and we have v. And we're given So we only have one given rate. So we're given one rate, and we have two variables. So we have two more variables than we do rates. So our situation works out nicely. We know that since we have the volume of a sphere, the equation that we're going to use is the volume of a sphere equals 4/3 pi r cubed, right? So two variables and one rate, one known rate. Okay. Step 5, implicitly differentiate both sides of the equation with respect to time. This is where page 119 comes in handy because we've already implicitly differentiated this volume equation. And we got that dv dt equal to 4 pi r squared dr dt. Okay, so now we want to substitute all instantaneous rates and volume and values of the variable and solve for the remaining rate or variable. So in the problem, we were told that at the instance when the radius is 4. So instance is this instantaneous point. So we want rate to be 4, the radius to be 4 centimeters. So we're looking at that instant, and we're trying to find dr dt. So dr dt is what we're looking for, and we have dv dt. So we're going to substitute all of that into our implicitly differentiated equation. So dv dt is negative 230 equals 4 times pi times r at that instance, which is 4 squared. And then dr dt is what we're looking for. Okay. Oops, it's negative 230 pi. All right, so now we're just going to solve for dr dt. That's the goal. So this is what we're trying to find. So we're just going to solve for it, get it by itself. So we have negative 230 pi equals 64 pi dr dt. So negative 230 pi over 64 pi equals dr dt. The pi's can cancel out. So we have that dr dt is equal to negative 230 over 64, which we can keep like this, or we can actually put in a calculator and estimate it to negative 3.5938. And our units are centimeters per minute. So the rate of change of the radius of the balloon at when the radius is 4 centimeters is going to be negative 3.5938 centimeters per minute. That's how the radius is changing when the radius is 4. Okay, so page 121, I'm actually going to have you do this problem on your own. And the reason for that is because it is very similar to the problem on page 120. So you're going to go through this problem in the same way we went through the problem on page 120. And you're going to do your best to figure out what the rate is, at what rate the total area of the disturbed water is changing. Okay? Page 122. So for page 122, we're going to do a good chunk of this problem together. We're not going to do the whole entire thing. I'm going to try and leave the last couple of steps to you. So for this problem, we have water is leaking out of a cylindrical tank at a rate of 3 cubic feet per second. If the radius of the tank is 4 feet, at what rate is the depth of the water changing at any instant during the leak? So after reading it, I'm just going to go through and annotate once again. So we hear that the water is leaking out. So again, this tells me I'm going to have some sort of negative value. And we're in a cylindrical tank, so we're looking at a cylinder. and we have a rate of 3 cubic feet per second. So the cubic indicates that we're looking at volume. That's not how you spell that. And since it's a rate, we know we're looking at dV dt. We know that the radius of the tank is 4 feet. And we want the rate the depth is changing. So when we're thinking about depth, we are talking about height, right? So if I'm looking at the rate of height, then I'm looking for dH dt. So the variables in this problem are radius, height, and volume of a cylinder. Okay, so when thinking about a cylinder, the variables that will remain constant, right? The radius of a cylinder stays the same no matter where you are in the cylinder. So my radius is my constant. And we're given what that is. So the R is equal to 4. So my constant radius is 4. Okay, so now we need to identify the rates that we're given and the rate that we wish to find. We're given dV dt, which we're told is 3 cubic feet per second. And we're looking for dH dt. And the units for that will just be feet per second. Okay, we're also told that water is leaking, so volume is decreasing. So the rate should be negative for that case. So now for part number 4, we want to write an equation. And we want to make sure that our equation only has one more variable than we do rates, right? So because we have one known rate, we should only have 2 variables. Okay, so what that means is if we look at number 1, we clearly have 3 variables. One of those variables has to be constant, which we've already identified to be the radius. So when we plug things in, we're going to have V equals, we're looking for the equation of a cylinder for a volume. So let's generalize it. It's pi r squared h, right? So here we have 3 variables, but we only have one known rate. So one of these variables is constant, so we'll rewrite it. V equals pi r, which is 4 squared h. So V equals 16 pi h. All right, so now for part 5, we're differentiating that equation, which we've already done on page 119. So it's just a matter of rewriting that, keeping in mind that we know the value of R, which was 4. And then substitute the instantaneous rate that we have, which is 4, right? Oops, I lied. Oh, we don't have an instantaneous rate in this problem. My bad. But we do have the dV dt, so we'll plug that in and solve for dH dt, since that's what we're looking for. All right. So on page 123, we have another problem. This one's going to be a little bit more work. We have a cone that has a diameter of 10 inches and a height of 15 inches. Water is being poured into the cone so that the height of the water level is changing at a rate of 1.2 inches per second. At the instant when the radius of the exposed surface area of the water is 2 inches, at what rate is the volume of the water changing? This is a little bit wordy. So we know we have a cone We know the diameter of that cone is 10 inches. So D equals 10. And that changes R to equal 5. And we know that the height of our cone is 15 inches. So H equals 15. Water is being poured out of the cone. Water is being poured into the cone so that the height of the water level is changing at a rate of 1.2 inches per second. So we have a rate here, and it's the rate of height. So we know dH dt is equal to 1.2. At the instant when the radius of the exposed surface area of the water is 2 inches, so we're looking at the instant when R is 2, at what rate is the volume of the water changing? So we are looking for dV dt. Okay, so this problem has a whole lot of variables. It started with diameter, but in the formula for a cone, we're not going to use diameter, we're going to use radius. So we have the radius, we have height, and then we have volume of a cone. Okay. So when thinking about the volume of a cone, the radius is different at any point on the cone, the height is going to be different on any point of the cone, and the volume is going to be different at any point on the cone. So there are no constant variables. Okay. However, we have the rates dH dt, which is equal to 1.2 inches per second, and we're looking for the rate dV dt, which will be some number, and since it's volume, inches cubed per second. Okay, so here's where we run into an issue, right? So for part 4, we know that we have only one given rate. So because we only have one given rate, we're only allowed to have 2 variables. However, we have 3. So since we're only allowed to have 2 variables, and we have 3, and not one of them is constant, that means we have to rewrite one variable in terms of another. So I'm going to sketch an image of this cone. So here's my cone. It's not a very good sketch, but it's all right. We have some radius, some height, right? We know that at the top of the cone, the radius is 5, and the height is 15. So there's a ratio here between the radius and the height, right? So radius to height is 5 over 15, right? So using that information, I can rewrite the radius in terms of h and the height in terms of r. Since we have dH dt, I'm going to rewrite the radius in terms of h. So I know that r over h is equal to 5 over 15. So r over h is equal to 1/3. So r is equal to 1/3 of the height. So what I'm going to do with that is I'm going to plug in 1/3 h in for r in my volume equation. So the volume of a cone is 1/3 pi r squared h. And I'm going to plug in 1/3 h in for r. So I have V equals 1/3 pi, 1/3 h squared times h. Okay, so simplifying, I get 1/3 pi times 1 1/9 h squared times h. So V, when I multiply everything out, is equal to 1/27 pi h cubed. Okay, so now, because I have made a substitution that relates one variable in terms of another, I've changed the formula a bit, which means I now have to implicitly differentiate, and it's not already on page 119. So I'm going to implicitly differentiate this volume formula. So I want d dt of v equals, and then 1/27 pi is a coefficient, so I'll bring that up front. And I want d dt of h cubed. So I'll have 1 dv dt equals 1/27 pi times 3h squared dh dt. That's not t. And when I simplify, that gets me to dv dt equal to 1/9 pi h squared dh dt. So now I have a formula and a derivative where I have two variables in my formula, and in my derivative, I know one of the two rates. So for part 6, now I'm going to substitute any instantaneous rates. So if you look back at the problem, we know that we're looking at the instant when the radius of the exposed area is 2 inches. So we're looking at the instance when r is 2. We know that dh dt is equal to 1.2. Okay, and since we know the ratio of radius to height, right, since we know that r is equal to 1/3 of h, so 2 is equal to 1/3 of h, then h must equal 6. So plugging in these three values into my differentiation, I'll be able to figure out what dv dt will be. So dv dt is going to equal 1/9 pi 6 squared times 1.2. So dv dt will equal 4.8 pi inches cubed per second. Okay, so on to page 124. A ladder, 25 feet long, is leaning against the wall of a house. The base of the ladder is pulled away from the wall at a rate of 2 feet per second. How fast is the top of the ladder moving down the wall when the base of the ladder is 7 feet from the wall? So this question I'm going to draw a sketch of what this problem is probably going to look like, right? So I have a wall, I have a ladder against it, I have a ground. Okay, so it's looking like a triangle. Right, here's my building, here's my wall. Okay, so it's looking like a triangle. I know I have a ladder that's 25 feet long and it's leaning against a house. We know the base of the ladder is being pulled away at some rate. And we want to know how fast is the top of the ladder moving down when the base is 7 feet. So let's label what we know. We know the ladder is 25 feet. We know the base, so I'll just call it B. The rate of the base, so dB dt is 2 feet per second. And we want to know how fast the top of the ladder is moving down when the base is 7. So we're assuming that we're looking at the instance when B is 7. So before we can really do anything with this triangle, we need to figure out what the missing side of our triangle length is. So we have 7 and 25, and we need to know what this side, I'll call it A, is going to be. So to figure that out, we're going to use the Pythagorean theorem. So we'll have a squared plus b squared equals c squared. So a squared plus 7 squared equals 25 squared. So a squared plus 49 equals 625. A squared equals 576. So a is equal to 24. Okay. All right. So the rate that we're looking for is dA dt. So if we look back to page 119, there's an equation already written to help us with this problem, right? So let's take a look back at 119 and look at the equation that we're going to need to use and what information we know about it. Okay, so the equation that we're going to use is A equals square root of c squared minus b squared. And we know that c is constant. And from our problem, we can tell because the ladder is not going to shrink in size, right? The ladder is going to be 25 feet long at all times. So knowing what we know, we're now going to differentiate this equation. And we know that the derivative of this, so dA dt, is equal to negative b over square root of c squared minus b squared dB dt. Okay, so dA dt is what we're looking for. Negative b. So we know that b is 7. So dA dt equal to negative 7 over c squared, so 25 squared minus 7 squared times dB dt. And dB dt, we're told, is 2 feet. Okay. So dA dt is equal to negative 14 over 24, which is equal to negative 7 over 12 feet per second. So now, for part B, we want to consider the triangle that's formed by the side of the house, the ladder, and the ground. Find the rate at which the area of the triangle is changing when the base of the ladder is 7 feet from the wall. So we have the same triangle from part A, right? We have 25 for our ladder. Our base is 7. Part A is 24 because we've already done the Pythagorean theorem for it. Our rate, we already know dB dt, which was 2. And we already know dA dt, since we just found it, which was negative 7 over 12. And these are both feet per second. Okay, so we have two known rates, and we're looking for the area, right? So we're looking for d capital A dt, and that'll be in the units feet squared per second. Right, so we're looking for the area of this triangle. We know that to find the area of a triangle, that's 1/2 the base, which we labeled B, times the height, which we labeled A, little a. Right, so we have 3 variables, 2 known rates. We're fine. We don't have to rewrite anything at all. So what we're going to do now is we're going to take the derivative of this equation. So we want d dt of A, big A, equals 1/2 d dt of B times little a. Okay. So over on the right side, the derivative of B times A, we're going to have to use product rule here because we have 2 different variables multiplied together. So we'll have 1 d capital A dt equal to 1/2 times 1 dB dt times A plus B times 1 d little a dt. And when we simplify that, we get d capital A dt is equal to 1/2 times A dB dt plus B dA dt. Okay, so now when we substitute everything that we know, we'll get that dA dt is equal to 1/2 times 24 times 2 plus 7 times negative 7 over 12. Which is approximately equal to 21.9583 repeating feet squared per second. All right, and then the last problem on this page, we want to find the rate at which the angle formed by the ladder and the wall of the house is changing when the base of the ladder is 9 feet from the wall. So again, we're looking at the same triangle. Ladder is 25. Now our base is 9. Okay, and we need to figure out what our A is going to be. So our A squared plus B squared equals C squared. So A squared plus 9 squared equals 25 squared. A squared plus 81 equals 625. So A squared equals 544. So a is equal to the square root of 540. All right. So in this problem, we want to know the rate at which the angle is changing. So we are looking for d theta dt. And we're looking for the angle formed by the ladder and the wall of the house. So that angle is going to be up in this corner. And we also know that the base is changing, right? So the base is changing, but we're looking at the instant when the base is 9 feet. So from page 119, the equation, sort of, that we're going to use is going to be a trig equation, right? So what we're going to do, since we know dB dt, we know the rate at which the base is changing. It's been the same throughout the problem. dB dt is equal to 2 feet per second. It's been the same throughout the whole entire problem. We're going to write a trig equation where b is one of my variables. Okay, so if I want b to be one of my variables using trig, we're going to use sine, right? Because 25 is a constant. And I want b to be one of my variables. So I'm going to have the opposite and I'm going to have the hypotenuse. So we're going to use sine theta and we're going to set it up. So b is changing and 25 stays the same. It's my constant. All right. But to do this problem, we're also going to need the cosine of theta. And I'll see why in a second. So the cosine of theta is going to be square root of 544 over 25. So the equation we're using is sine theta equals b over 25. So I'm going to rewrite that so that it's sine theta equals 1 over 25. And then I'm going to differentiate that. So I want d dt of sine theta equals 1 over 25 d dt of b. So the derivative of sine theta is going to give me cosine theta d theta dt equals 1 over 25 times 1 dB dt. Okay. So simplifying that, we have cosine theta d theta dt equals 1 over 25 dB dt. And we're going to substitute everything we know. Okay, so what that means is that cosine theta, we know what that is. dB dt, we know what that is. So we have square root of 544 over 25 d theta dt equal to 1 over 25 times 2. And since we want d theta dt on its own, we're going to flip this. So d theta dt will equal 1 over 25 times 2 is just 2 over 25. Keep change, and we're going to divide by square root of 544 over 25, so it's multiplying by 25 over square root of 544. So the 25s will cancel each other out. And we have d theta dt is 2 over square root of 544, which can simplify to square root of 544 over 272. And our units are radians per second. Okay, so moving on to our very last page, page 125. We have 3 problems. And what I actually want you to do is I want you to try the first 2 problems on your own. They might be a little tricky. The first problem is an airplane problem that you will use Pythagorean theorem to help you solve. The second problem is a sphere problem that you'll use the surface area of a sphere to help you figure out. The last problem is another sphere problem. But the reason why we're going to do this problem together is because you use 2 different functions to help you figure it out. You need the surface area and you also need the volume function. So for this last problem, we have a spherical balloon that's expanding at a rate of 60 pi cubic inches per second. So it's a rate with cubic inches per second. So this is going to be our dV dt. How fast is the surface area of the balloon expanding when the radius of the balloon is 4 inches? So we have radius equals 4, and we need dA dt, the rate of the surface area. Okay, so there's a few problems with this problem. We don't have a lot of information. We have 3 variables: volume, surface area, radius. We only have one known rate. So we have dV dt, which is 60 inches cubed per second, but we don't have dr dt, and we don't have dA dt, which is exactly what we're looking for, right? So we want dA dt, which is some number inches squared per second. But in order to do that, we also need dr dt, which will be some number inches per second. So we are going to need to rewrite a variable in terms of another variable, or identify what one of those rates will be. So what we're going to do is we're going to set up both equations. We're going to set up the equation for volume and the equation for surface area of a sphere. The volume of a sphere, 4/3 pi r cubed. Surface area of a sphere, 4 pi r squared. We've already done the implicit differentiation for both of these, right? The derivative of volume, it will be dV dt equals 4 pi r squared dr dt. And the equation for area will be dA dt equals 8 pi r dr. So what we're going to do is we're going to solve one equation for dr dt and then use dr dt in the other equation. So since we're looking for the area, the rate of the surface area, we're going to save the area function for last. We're going to work with the volume function first. We know dv dt, that's 60, equals 4 pi, and the instant rate that we're looking for is 4 for the radius. So 4 squared dr dt. So solving for this, we have 60 equals 64 pi dr dt. So dr dt is equal to, this is 60 pi. I always make that mistake. So it's equal to 60 pi over 64 pi. Pi's will cancel out, and we'll be left with 60 over 64, which is just 15 over 16 inches per second. So dr dt is 15 over 16 inches per second. So now that we have that information, we can plug it into our surface area derivative. So we have dA dt equal to 8 pi, our radius is 4, and our dr dt is 15 over 16. So dA dt is equal to 480 pi over 16, which is equal to 30 pi inches squared per second. So as the volume of this balloon is increasing by a rate of 60 pi cubic inches per second, the surface area is increasing at a rate of 30 pi inches squared per second. Okay, so like I said, I want you to try the 2 problems on this page to the best of your ability. And you should be able to now complete the homework problems number 9 through 28.